Okay, so let's take a look at Pythagorean theorem in 3 dimensions. All right. This particular skill is a little bit trickier than just looking at it in 2 dimensions. And one of the main reasons for this is that most of the time you're going to be asked to apply the Pythagorean theorem twice, not just once, but twice. To help you along the way, Khan Academy has provided you with a calculator. I strongly suggest that you use it. It is going to make your life easier to solve some of those square roots that we get from our Pythagorean theorem. So without further ado, let's take a look at this. Reading the question very carefully is probably also a good idea, and trying to analyze what you've actually got. If you are so inclined, I would strongly suggest that you might also go online and search for a template for you to be able to create a paper model of these shapes. So if you're asked for pyramids, maybe creating a paper model of the pyramids, noting that this particular pyramid is taller than the base, and the bottom pyramid looks like it might actually be of equal sides. In fact, it is of equal sides. But making a paper model and actually looking at it from the 3-dimensional point of view might also help you. All right, let's look at the information that we have. We have the vertical height of the top right pyramid. Okay, so talking about a right pyramid, it's creating right angles down on the base, is what it is. So what is the vertical height of that top right pyramid? Well, if you think about that, if you were to go into the center, right into the center in here, which is really the center of this base square here, okay? If we can actually find that center there, and we can create a line straight down through the middle. Now, it's harder to see this in 2 dimensions when you're supposed to be looking at a 3 dimension. So if you've got a model, take a look at this. You're really looking right down through the point of it to the very center of the base, and that there is a length of 7. Okay. We're told that the height of the bottom pyramid is 3. So from that same point, okay, the height of the bottom pyramid is 3. So from that exact same point, we can draw a line straight down to the point of the bottom pyramid, and that there is 3. Okay, interesting. So we're going to complete height of 10 units. The square base of both pyramids has side length 3, and this is kind of important. So the square base of both pyramids is side length 3, and this is the base I was talking about a moment ago. If you have this square base here, and as you can see, it's kind of lying flat, so it does not look square right now, but each of these side lengths has 3 units, which means that this little side length here that we talked about a moment ago, if you go from the center of one side straight into the middle, well, that is half of 3. That is 1.5. Okay, and we can actually do that from any of the sides. Right? How you draw it is really the key. Okay, so just to extrapolate that side there, let's take a look at the square base. Okay, and what I'm saying is the square base is 3. And the center point right there is where those two heights are joining. So if we were actually to create a line in from the center here, we've got 1.5 here, and we end up with 1.5 here. So what I'm really doing is I'm using that to create a right-angled triangle. Okay? We're being asked, just so we can clarify, we're actually being asked for this side length S. So we're being asked for the side length S. Now, before we ever get there, we need to solve a couple of things, and really, to observe that side length S is going to be the same as this side length. It's going to be the same as that side length, and of course, it's going to be the same with that back side length back there as well. Okay, that's way back there. Okay, and as you can see, that side length comes to the corner of this square, and it goes right to the very tip. Okay, so let's look at our triangles. We got, first of all, we can't even solve that triangle. We can't solve that without first getting more information, because the side length S, sure, we have a side length of 3 to work with, or 1.5 if we deal with half of it, but we need another side length to be able to get it. I mean, we can't even begin to figure it out without having another side length. So let's get that other side length. What I'm going to propose is that we use the Pythagorean theorem to solve the side length, the length of the inside of one of these triangles. And how I'm going to propose we do that is by using this as the base, which is the line that goes from that center point straight into the middle. So this line here that I was talking about earlier, so I'm going to say we use that as the base, that is 1.5. Okay, we use the height, and we can choose 7 or we can choose 3, it doesn't really matter, but I'm going to choose the red height, the 7. And I'm going to say, well, let's find out what this here is. Now, just to be careful, that is the height of that is the side, that is the middle of that triangle. It's not the side length S. This is the line that actually ends right here. It comes from the tip and it ends right here. And the reason why I'm choosing that is because if I draw a line straight down, if I was to take this side triangle here, and if I was to draw a line straight down, I'm creating a right angle here. Okay? And by creating that right angle here, and knowing that I've got a base of 1.5, I can then find out what S is. Okay? So I'm going to use both of those together. Okay. So let's set up the Pythagorean theorem. We have, based on this interior triangle here, we have c squared equals a squared plus b squared. I'm going to say that this is a and this is b, so equals 7 squared plus 1.5 squared. And in fact, I'm going to go one step further right from the very beginning, because we've done this already on our basic Pythagorean theorem. So rather than saying c squared, I'm just going to say c, and I'm going to take the square root of the answer, and that is going to get me back to where I want. Okay, so c is equal to the square root of 49 plus, and let's use our calculator real quick. 1.5 times 1.5, that's 2.25, which should make a lot of sense to you because 15 times 15 is 225. Okay, so we've got plus 2.25, which means that we have 51.25. And I'm going to suggest that we do not actually take this out of the square root sign, out of the radical, because this is going to be useful to us later. And this length here is what we've got right here. Okay, so we have 51.25, we've got 1.25, we've got 1.5, and we have S then is equal to the square root of, now let's look at this carefully, we've got 51.25 squared, so let's just unsquare that, that's the square root, we're just squaring that, which means we just cancel out the squares, so that's just 51.25. And 1.5 squared we learned was 2.25. Okay, so that is the square root of 53.5. Okay, so S is equal to the square root of 53.5. We're being asked to round to the nearest tenth, so let's do that. Let's first get our square root. Let's get our square root of 53.5. And that's going to give us 7.314, etc. So we're just going to round to the nearest tenth, 7.31. I hope that was helpful to you. If you've got any questions, please come see me. Bear in mind that with the Pythagorean theorem in 3 dimensions, you're almost always going to be asked to apply the Pythagorean theorem twice.